Now in this video, now let's talk about the change of shear force and the change of bending moments. So we'd like, if you plot the change of shear force and change of bending moments, so we call that diagram shear force diagram and the bending moment diagram. So if I write in full word, this is called shear force diagram. In 우리말, we call it 전단력 선도. Okay? And then the BMD, bending moment diagram. Bending moment diagram. Moment 선도. Sometimes we call 힘 moment 선도. Anyway, same meaning. Okay, 전단력 선도 and moment 선도, 힘 moment 선도. We simply call SFD and BMD, the shear force diagram and bending moment diagram. Okay. So now here, let's talk about the construction of shear force and bending moment diagram. So make sure that I didn't say, the calculation of shear force diagram and the bending moment diagram. So here I know the procedures, construction. The meaning of construction is actually any calculation is very minimized. Okay, we have very minimal amount of calculation to draw the shear force diagram and the bending moment diagram. Okay, trust me. So we don't need a very complicated calculation as given in the textbook. You don't need that. Okay, we just construct shear force diagram and bending moment diagram, the following the equation that we derived in the last lecture, no? Where we discussed the change of shear force and change of bending moment caused by the external forces. Here, as I told you, the shear force diagram is nothing but change of the distribution of the internal shear force along the longitudinal direction of the beam member. That is called the shear force diagram. And the bending moment diagram is the counterpart of that distribution for the bending moment. Okay. And then here, the construction of these two diagrams should satisfy the equilibrium equation. So we already derived how to calculate the change of shear force and change of bending moment, okay, using the area calculation. Okay, so now let's talk about how we construct the shear force diagram and the bending moment diagram using a specific example. As the first example, let's consider a simple problem here. Alright, so here let's consider a simply supported girder here. So if you consider simply supported girder, and the first thing that we have to do is we have to determine the reaction here, isn't it right? So let's check the force equilibrium, then we can easily determine the reaction. The reaction is equal to what? Reaction is equal to by the proportional relation, this is B over L times P, this is RA. And the RB is equal to A over LP. Okay, so I just used the moment equilibrium. For instance, here L times RB. So if you choose the reference point for the moment calculation at point A, then this is equal to A times P. Okay, so if you move L to the right hand side, we can determine the reaction acting on point B. Okay, point B. And then once we have the information about B, then we can determine the RA using the force equilibrium in the vertical direction. And please note that this is hinge support. In the case of hinge support, hinge can resist the horizontal force component too. But we don't have any force in the horizontal direction. That's why here we don't have any reaction component in hinge support. Although the hinge can resist both force in the horizontal direction and force in the vertical direction. Okay, so now we just determine the reactions. Okay, so now let's focus on our structure here. So in our structure, so this is our structure. On the left hand side, we have force upward here, RA. Okay, and then we have RB here. and then I have loading. Okay, what is the sign convention of shear force? The sign convention for the shear force is what? So if we have any upward shear force on the left hand side of segment, so we call it positive shear force. And then if we have the shear force on the right hand side should go downward, this is positive one. Okay, let's look at this guy. This is goes up, isn't it? This guy goes up on the the left side of the beam. That's why this is positive. So the height here is equal to what? RA. Okay, we start with RA, and then up to this point, for example, let's consider here. The change of shear force is equal to minus the area of the distributed load dV, sorry. The change of shear force is the area of distributed load here. So, but there is no distributed load, so which means there is no change of shear force. That's why we have this horizontal line. Clear? Okay. Then I have concentrated load here. So once we have concentrated load, then let's go back to our lecture slide here. If we have any concentrated load, the change of shear force is minus of the magnitude of force P. So let's refer to that equation. And then we have certain change in downward. The size is equal to P, isn't it? So downward change. The sign of internal shear force is positive, and then because it changes by P, we have negative value of the internal shear force. And then here, once we touch here, we have another the force upward. According to sign convention, this is is going up, but in the case of positive one, it goes down. That's why this guy is minus. So minus internal shear force here, whose magnitude is equal to what? RB. Okay, this is the distribution of shear force. This is called the shear force diagram, SFD. So now let's try to construct the bending moment diagram. Please make sure that the change of bending moment between 2 points is given by nothing but just area of shear force diagram, isn't it? Right? Change of bending moment is given by the area of shear force diagram. It's so simple. So now let's try to calculate the change of bending moment between these 2 points, the point here and the load point. Okay, so because the reason that I choose here, there is certain change, change of shear force diagram. That's why I choose this. So I want to calculate the change of bending moment between these 2 points. So according to this equation here, for example, let's revisit this equation to recall your memory. The change of bending moment is the area of shear force diagram. So now let's try to calculate the area. So how do you calculate the area? The area of shear force diagram is here. This is the area. Calculation of area is what? The length here is equal to A, and then the height of this rectangle is given by P and B, isn't it, right? So this is the area. So change of bending moment, because make sure that this is hinge support. At hinge support, there is no external moment. External moment is equal to 0. So we start with 0 internal bending moment, and then the change is what? The positive of PAV divided by L. That's why we have positive value. Okay, we just determine this point. Okay, we just determine this point. We start from the 0 internal bending moment, and we just determine the change of bending moment should be given by delta M is positive of PAB divided by L. Okay, make sure that this is positive bending moment. And then make sure that we just calculated these two values, but we never determine how it changes. Again, let's revisit this equation. The change of bending moment here, the slope of bending moment is equal to the shear force. Okay, so the slope of bending moment is equal to shear force diagram. So shear force here in this region is constant. Okay, then what has constant slope? What function has a constant slope? Linear or quadratic? In the case of quadratic equation, the quadratic equation has the linear slope change, isn't it? But in the case of linear function, it has a constant slope. That's why the bending moment diagram between these 2 points, we connect these 2 points with a linear line. Isn't it clear, right? So make sure that this slope is equal to the shear force here, which is equal to, in this example, PB over L. Okay. What's the next point? So now because we just determined the bending moment here, so now let's determine the change of bending moment between these 2 points. Okay. So let's take this. Then how do you do that? Again, the change of bending moment between 2 points is nothing but just area of shear force diagram. So area of shear force diagram, this area. Okay, and then its length is what? Its length is equal to B times, and height is equal to RB. So we have information of RB. B times AP over L. Now what is the sign? This is minus sign. So we have the bending moment minus change. So my bending moment drops from PAB over L by this quantity. If you consider this change, then consequence is what? The bending moment should be equal to 0 at this point. So let's check. If you look at the loading condition here, there is no external moment. So we can conclude that our calculation is correct. It's very easy, yeah? That's why I call it construction, okay, construction. So we just construct shear force diagram and bending moment diagram following the rules that we derived just before, okay? Let's consider another example. This is the case with the distributed load, okay? Again, as usual, what we have to do is we need to calculate the reaction first, okay? Alright, so let's check the force equilibrium. The force, overall force caused by the distributed load. Here, let's assume the Q is constant. Then Q times L is the total amount of external load. And then, because we have two support, the RA is equal to a half of QL, and the RB is also equal to a half of QL. Okay, so at first, so now let's construct the shear force diagram. So we start from here. And then there is a change of shear force by what? So according to the sign convention of the shear force, this is positive. We have a certain change of shear force by a half of QL. Okay? And then let's check the change of shear force between these 2 points. Because between point A and point B, I have constant the distribution of constant distributed load Q. So if you do that, nothing but just area calculation. The area calculation is what? Area is equal to the L times Q, isn't it, right? So L times Q. So from this point to this point, so we have the change by L times Q. But its sign is minus, okay, minus. So, and then let's check this equation here. If you do that, the change of shear force diagram, the slope of shear force diagram is given by the function of distributed load. Okay? So look at this. The slope of shear force diagram should be given by the distributed load Q here. Now is Q is constant, which means my shear force diagram is linear. That's why we draw a straight line between these 2 points. Is it clear, right? It's very easy, right? Very easy. And then at point B, we have upward force. According to the sign convention of internal shear force, this is minus value. Okay? Sorry. This is plus. Yeah. That's why we have shear force. And then this is plus and minus. It's so easy. This is nothing but construction. And now how do you determine where the shear force is equal to 0? Starting from here, a half QL, so we find the length, which makes internal shear force is equal to 0. That's very easy, right? So now next step is I wanna determine the bending moment diagram. So here the starting point is here. There is no moment reaction. The external moment is equal to 0 to the beam structure. So we can start from 0 moment here, and then I want to change of bending moment between these 2 points. Okay. So according to our equation here, the change of bending moment is what? The change of bending, where is it? The change of bending moment is nothing but just area of shear force diagram. Keep in mind that equation. Then we calculate this area. This area is what? How do you calculate this area? A half times the length is a half of L, and because this is triangle, and then the height of the triangle is equal to a half QL. Okay, that's why we have this value, 1/8 of QL squared. So we can determine this point. This is change. Okay, this change is given by this equation. Because this is positive sign, the change of bending moment is positive. So now, as I told you, we just determine these 2 points. Okay, we never determine how the function changes, how the bending moment diagram changes. Like this, whether like this, or we have this convex shape or concave or whatever, isn't it, right? But here the clue is here. So if you look at the shear force diagram is linear. The linear means the slope is linear means my bending moment diagram should be quadratic, isn't it? So we can determine it's a quadratic one. So there are 2 different kinds of quadratic. One is convex, or the other one is concave one. Whether it's convex or concave. Okay, let's check one by one. If you want to say this is a convex one. Convex means here we have small slope. We have small slope and we have bigger slope. Small positive slope and a big positive slope. So let's check the shear force diagram. Then if you check the shear force diagram, the slope, the internal shear force value at this point is equal to 0. And then we have maximum slope at this point. That's why this choice cannot be the shear force diagram. So here, shear force value at the center is equal to 0, which means the slope of my bending moment should be is equal to 0. It's horizontal. And then at this point, I have maximum slope here. So make sure that the amount of the tangent at this point is equal to a half of QL. Is it clear, right? So considering these 2 aspects, the slope at the center is equal to 0, and at the support is maximum, and then the function is quadratic. Then the only solution which is satisfied the above mentioned condition is this concave upward. Okay, is it clear, right? And then also let's check the other remaining part. Also look at this. If you look at the shear force diagram is equal to 0 in the other center. That's why we start from the 0 slope, and then we have minimum the slope. That's why we have this curve. This is the construction procedure. It's very easy, right? Okay. And then let's consider another example. Again, similar to this, first we need to calculate the reactions. Okay, these two reactions, and then we start with the first reaction here, and then in the segment A1, there's no change in the shear force diagram, and because we have a concentrated load, the shear force diagram drops by P1, and then also there's no change before we have the next concentrated load, and then it drops by P2, and then by P3, and also it recovers to the 0 point. The sign is positive and minus. And then let's try to construct the bending moment diagram. It starts from the zero bending moment. Again, as I told you, we need to calculate the area of shear force diagram. Here we need to calculate this rectangle, and that's constant. That's why my bending moment diagram is straight line. Okay, and then again, next small rectangle is another straight line, the negative straight line here. It's very easy, right? Now let's consider pure bending case. Pure bending problem, we have M1 and M1 on left hand side and right hand side. And then if you calculate the reaction is equal to 0. My shear force diagram is 0, the flat, it's just 0, no change. And because I have one external bending moment, it starts from M1, okay? And then this is positive, and then horizontal line. This is a pure bending moment case. So let's consider, this is called 4-point bending, because I have point 1 and 2, 3, and 4. And this is called 4-point bending. Let's calculate the reaction. This is P, and then also I have P. Then we can construct the shear force diagram. Now, how do you construct shear force diagram? We can start with P, and no change before we have external load, and then P, and drops, positive. And then no change in the middle, 0, and then shear force minus here. The height is equal to P, and also equal to P, isn't it? So now let's try to construct the bending moment diagram. We start from the 0, and then we need to multiply the length to the height of the P. It increases. The height of the bending moment diagram is P times A, isn't it? Then here the shear force is equal to 0. Shear force is equal to 0 means there is no change in the bending moment in this region, the whole flat, and then also linear curve, positive. So this region is pure bending moment, okay, pure bending moment. Because of this reason, to reproduce pure bending moment condition, often we use 4-point bending test, even for concrete specimen. Okay, then in this region we have pure bending moment condition. Okay, and then you may want to consider more examples to understand this problem. So maybe you want to work with my TA for some more examples. So here I'd like to consider one more examples with internal support condition. Okay, here. So how can I rotate it? Okay. Okay, so let's consider a cantilever problem. So I have a cantilever. And then its length is equal to, for example, 2 for simplicity. And then I have an internal hinge. And then I have another segment. But this segment is supported by a roller here. And then let's consider a distributed load. Its magnitude is equal to 1. The free segment, its length is equal to 1. So let's notice point A and point B and point C. At the very first step, we need to calculate the reaction, isn't it, right? So we need to figure out what kind of reaction. We need to have here RA, and then also we need to consider the moment at point A, and then at point C, we must have RC. In total, we have 3 different unknowns, isn't it? So let's look at segment BC first. If you look at segment BC. So if you look at segment BC, and then this is a hinge, isn't it? Hinge means there is no internal bending moment to resist. So there should be the hinge, but the transfer the shear force. So if you consider free body diagram, I have distributed load 1, and then I have RC. So let's check the moment equilibrium with respect to point B. Let's check the moment equilibrium. Sum of moment should be equal to 0 here. So then RC times 1 is equal to, so 1 times 1, the magnitude is equal to 1, length is equal to 1, the arm length is a half, isn't it? So it is equal to a half. So we can determine RC very easily using the moment equilibrium for this segment. Isn't it, right? So we just finished the determination of RC. So once we have the information of RC, then we are ready to determine the information of RA. Let's check force equilibrium in the vertical direction. Then by the external load, we have 1 times 1. And then by the reaction at point C is equal to a half. That's why remaining is equal to a half. Okay, this is determination of reaction at point RA. Now let's check the moment equilibrium for the whole structure. So let's consider the moment equilibrium of the whole structure. So let's check moment equilibrium, the sum of moment, so MA, and then because if you choose the reference point at A, then contribution of RA to the moment is equal to 0 because the arm length is equal to 0. And then plus the moment contribution of RC is what? The arm length is equal to 3 and this magnitude is equal to a half. So 3 times a half is 3 over 2. And then how about this guy? The external load is magnitude is equal to 1. And then the arm length is what? 2 plus a half. Okay? Times is equal to 1. And then its sign is what? Its sign is minus. Okay? And this is equal to 5 over 2. Then if you finish the calculation, then MA is equal to 5 over 2 minus 3 over 2. This is equal to 1. So the MA is equal to 1. Is it clear, right? This is determination of external, the reactions of this beam problem. So now next step is we need to construct the shear force diagram. The next step, let's construct the shear force diagram. Let's do that. So we prepare a space for this job. First we have reaction RA1. Then we increase the shear force diagram by a half, okay, a half. And then there's no change up to point B in the shear force diagram, isn't it, right? And then between point B and point C, there is a change, isn't it, right? How do you calculate the change? This is nothing but just area. Area is equal to 1, but its sign is minus, isn't it? So that's why the change between these 2 points, we have change by minus 1. Okay? This is positive shear force and a negative shear force. And then finally, we finish our calculation by factor or half of RC. So this is correct for the determination of shear force diagram. So next step is to make sure that at the hinge point here, at the hinge point, even at hinge point, if you look at the hinge point, I have a non-zero shear force here. Hinge can deliver, transfer the shear force. Now next step, let's try to construct the bending moment diagram. So bending moment diagram. We prepare a space for the job of bending moment diagram. Now we start with MA is equal to 1 here. According to sign convention of bending moment, that produces negative bending moment. It starts with minus. The height is equal to 1, its sign is minus. Okay, so now let's check the change of bending moment between point A and point B. So it starts from minus 1, but if you calculate this area, let's try to calculate this area. This area is, I'm talking about this area. The length of rectangle is equal to 2. The height is a half. So the area is equal to 1. It starts from the minus 1 of the bending moment, and up to this point we have plus positive 1 change. So at this point, internal bending moment is equal to 0 here. Okay? And how about the change of the bending moment diagram? That is determined by the shear force diagram, because the shear force diagram is the slope of the bending moment diagram. But here, make sure that between these 2 points, the shear force is constant. That's why we can determine the bending moment diagram is a straight line. And then the sign of shear force is positive, which means the slope is positive too. That's why we can determine the bending moment diagram using a positive straight line here. Is it clear, right? And then again, let's determine the change of bending moment up to this point. So up to this point, I have positive shape of bending moment, and here it starts with large slope, and the final slope is equal to 0. So that's why we have quadratic equation, and then it drops to 0 here. This is the construction of bending moment diagram. It's very easy, right? This is the case with internal bending moment, internal hinge. We can consider various problems. Another problem that we want to consider is, for example, let's consider another cantilever. But I have, in this time, I have a slide connection. Alright, now let's consider another problem with, instead of internal hinge, here I want to consider slide connection for the cantilever problem. So here let's consider the same cantilever, and here the length is equal to 2 before we have slide support. And then we have additional segment connected to this slide support, and it is supported by a roller. And then I want to denote this is point A and point B and point C. There must be the reaction RC and then RA here, and also reaction moment MA. And then, as I told you, the length of the segment is equal to 2, and then 1. Here, the force external load is equal to 1. Okay, so now let's check the force equilibrium of segment BC to determine the reaction RC. Sorry, we have RC here and the slide support. Make sure the slide doesn't transfer any internal shear force. That's why there is no vertical shear force for this segment BC. But it can transfer the internal bending moment. That's why there must be, we need to consider certain kind of bending moment here. So now we want to check the force equilibrium. We have external force here. If you check the force equilibrium in the vertical direction, we can easily determine that RC is equal to 1, isn't it? So vertically external load 1, and we have internal, the reaction in upward direction. That's why its magnitude should be equal to each other. RC is equal to 1. Okay, we just determine the reaction RC. So now let's check force equilibrium for overall system, the entire system. I'm talking about the force equilibrium for the overall system. If you do that, we can easily conclude that RC, because according to the force equilibrium, the horizontal vertical direction, it is already satisfied. RA is equal to 0. And how about moment equilibrium? So moment equilibrium, if you choose the moment equilibrium at point A is equal to 0. So I have one concentrated moment, the reaction, unknown moment, MA. And then the moment contribution by RC is what? Its arm length is equal to 3, and the magnitude is equal to 1. And then the moment contribution by the external load is arm length is equal to 2, and it's equal to 1. Make sure that its direction is opposite, that's why it's minus sign. Should be equal to 0. Then we can conclude that MA is equal to minus 1. Now, so MA is equal to minus 1. Okay? So now let's prepare a space for the job of the construction of shear force diagram and bending moment diagram. Let's prepare a space here, the shear force diagram. And then we start with 0. So RA is equal to 0. There is no change up to point B. So make sure that the shear slide cannot transfer the internal shear force at this point is equal to 0. And then we have concentrated load 1 here. Just beyond point B, we have one concentrated load in downward direction. That's why our shear force changes by minus 1. This is minus, and then there's no change before we meet point C, and then we have 1. Okay, this is equal to 1. This is shear force diagram. And then now let's try to draw the bending moment diagram. Okay, let's first prepare the space. I don't know how to use this. Oh, hold on. And then space. And then we start with non-zero bending moment. Please make sure that we have non-zero bending moment. Okay, we have non-zero bending moment. So if you check the numeric value, it's minus 1. But what is important is the default sign convention that we assume is according to the global coordinate system. But we are drawing the internal bending moment. The minus means it's not in this direction, it's opposite direction, like this direction. This means in the sense of internal bending moment, this is not minus, this is positive bending moment. This is very important one, yeah? We start with positive bending moment, whose magnitude is equal to 1. Okay? And then up to point B, there's no change in the bending moment, and the positive bending moment whose magnitude is equal to 1. And then I have negative change in the shear force. So 1 minus 1, then it drops to 0. This is bending moment diagram. Okay, here we discuss several problems regarding the construction of shear force diagram and the bending moment diagram. Actually, it is very easy, and the procedure is really straightforward if you understand the nature of change of shear force and the change of bending moment. Okay, so let me stop my video here.